Hello everyone, today we're going to talk about the Fourier series. The prerequisites for this material are calculus, in particular complex numbers, and linear algebra, in particular orthogonality, basis, and projections. Our motivation is signal processing. A signal is any structured object of interest, such as images, audio, video. They are modeled as functions of space, time, or some other variable. Finding adequate representations for these functions is crucial in many data analysis applications. Here we're going to use a running example that is an electrocardiogram, which is a measurement of voltage across time that is relevant to heart activity, to monitoring heart activity. As I said, we're going to model signals as functions. Here in particular, we're going to consider signals on a finite interval of the real line. The inner product between such signals is just equal to the product between the two signals, and we take the complex conjugate of one of them. Notice that we're considering complex valued signals or functions. We will see in a moment why we need to consider complex valued functions, and we integrate the product over the interval. We're going to be interested in sinusoidal functions. These are functions that oscillate at a certain frequency. So here, this is actually a function of time, which is the variable t. When interpreted as a function of time, this function is actually periodic with period 1 over f, where f is a parameter that determines how rapidly the function fluctuates. So let's prove quickly that this function is indeed periodic with period 1 over f. If we shift t by 1 over f, what happens is that we're shifting the argument of the cosine by 2 pi, and we know by basic properties of the cosine function that cosine of like t is just equal to cosine of t plus 2 pi. So because of this, when we shift here, when we shift the function here by 1 over f, the value does not change. So the function is periodic with period 1 over f. If we draw a picture of a sinusoid like this, then basically the period is this. So this would be 1 over f. If we increase f, the period decreases, so the function fluctuates more rapidly. That would be higher frequency. If we decrease f, the period would be longer. The sinusoid would fluctuate more slowly. Okay, so that would be lower frequency. The amplitude just tells you how large these values are. This would be the amplitude A. And now I would like you to think about, of course, this is a function of time. I would like you to think what happens if we change the phase theta. Does it change how fast the function fluctuates? So think about it for a moment. It actually does not. When I ask you a question like that, by the way, feel free to stop the video and think about it for a bit. It does not. It doesn't change how fast the function fluctuates. It just shifts the function by some constant amount. Okay, that's the effect of this phase parameter. Okay, so now what we're going to want to do is to represent functions in terms of sinusoids in order to separate components that correspond to different frequencies. And for that, basically, we're just going to include, build a family of sinusoids that have different values of f. The issue is that we need to also take into account that such sinusoids could have different values of theta. So we need a way of efficiently representing sinusoids with arbitrary phase shifts, because otherwise we would have to include also sinusoids with different phase shifts in our family of functions, and that could become very inefficient if you just start adding arbitrary shifts. So the question here is, how do we represent sinusoids with the same frequency but different phases? And a very convenient way of representing such sinusoids is by using complex sinusoids. And this is the reason why we use complex functions in Fourier series, even though we often apply them to real valued functions. The reason is that you have to account for phase shifts in these sinusoidal components, and using complex sinusoids just makes life super easy. You could do this in an alternative way, which would be to use both cosines and sines in the representation, but things become very cumbersome, like even the notation becomes really cumbersome. So instead, we pay the price of dealing with complex valued functions, which might be a little bit complicated at the beginning, but we, as you will see, we obtain a very elegant framework. Okay, so what is a complex sinusoid? A complex sinusoid is a complex valued function that is equal to, well, where the real part is equal to a cosine and the imaginary part is equal to a sine. Let's take a look at a picture. So this is the real part, this is the imaginary part, and you see that the function varies on the complex plane and essentially just rotates in the complex plane. The reason for this is that if you think of the module of the complex sinusoid, okay, the module of the complex sinusoid squared is equal to the real part squared plus the imaginary part squared. But if you remember your, like the basic properties of cosines and sines, the square of the cosine plus the square of the sine is always equal to 1. So this is why you see the value of the complex sinusoid just rotating on the complex plane across time in this corkscrew manner. Intuitively, what we're doing here is we're encoding two sinusoids with the same frequency f, but with different shifts, because a sine is just a shifted version of a cosine. We're encoding them in the real and the imaginary parts. Okay, so now we're going to show why we're doing this. The reason we're doing this is that this is going to allow us to represent sinusoids with arbitrary phase shifts in a very convenient way. So first we need an intermediate result where we're going to take a look at what happens if we have exponential of minus I2 pi ft minus I theta compared to exponential of I2 pi ft plus I theta. Okay, so just by definition, we have that is equal to this. And now we're going to use the fact that cosine of minus x is just equal to cosine of x, and sine of minus x is equal to minus sine of x. So basically, this can be changed to plus, and the minus will come out. Okay, so bear with me, you'll see in a moment why this is important. Now we just sum both sides of these two equations, and we end up with the following result. We can express this cosine that has this arbitrary phase theta in terms of this average of these two complex exponentials. What have we gained, you might ask, because we still have the phase here. What we have gained is that now, because the exponential of a plus b is just equal to the exponential of a times the exponential of b, the phase comes out as these two multiplicative complex coefficients, so that now the phase is encoded in the complex amplitude of these complex sinusoids, and we have managed to express a function with arbitrary phase, so a sinusoid with arbitrary phase, in terms of a linear combination with complex coefficients, but that's fine, a linear combination of complex sinusoids which are independent from this phase. Okay, the phase is completely encoded in the coefficients with which we're weighting these two. You can think of them as basis functions. So basically, there's a linear subspace spanned by these two basis functions that contains all real sinusoids with frequency f. And that's very nice, because now we can just use these two functions to represent sinusoidal components that have that particular frequency, and we know that we will be able to account for any possible phase shift by just varying the coefficients. So now let's be a bit more concrete about the family of complex sinusoids that we're going to consider. We're going to be interested in a certain interval of length t. Okay, so let's say that it starts at 0, so from 0 to t. And now we want to consider sinusoids that live that space. Okay, so what we do is we consider sinusoids that have frequencies equal to k over t. So let's see what this means. This means that, for example, for k equals 0, think about what that function looks like. But for k equals 0, basically we just have a constant function, right? Because that's what the complex exponential when you have 0 equals to. When k is equal to 1, the period of the complex exponential is going to be exactly t. So then you're going to have some sinusoid that has exactly period t. Of course, here I'm drawing a real sinusoid. In fact, we have this complex sinusoid that has a real part and an imaginary part. Okay, but I cannot draw this corkscrew thing. So I'm just going to draw real sinusoids just so that you get an idea of the frequency that we're considering. We also have k equals to 2, okay, as we go along, because k is an integer. And for k equals to 2, basically what would happen is that we have 2 periods within t. If we have k equals to 3, higher frequency, 3 periods within t. And for arbitrary k, it's k periods within t. Okay, so we're essentially considering sinusoids that have increasing frequencies where their periods are always a multiple of t. Okay, so t, 2t, 3t, and so on. This is the family of sinusoids that we're going to use to represent functions that are restricted to 0 and t. Okay? So now we're going to see that these functions have a norm equal to square root of t, and more importantly, they are orthogonal if their frequency is different. Let's prove this, and then we will see what the implications are when using them to represent signals. Okay, so this is the inner product between a complex exponential of frequency k and frequency j, just by definition. Now the product of the exponentials is just equal to the sum. Now we see here if k is equal to j, then this is equal to 0, so that the exponential is equal to 1. In that case, we have this result where phi k is equal to t. But this is just the square norm of phi k. Okay, so that shows that. Now, if k is different to j, when we apply the antiderivative, and the antiderivative of the exponential is just the exponential, where like this constant has to come out, and we plug in 0 and t, what we get is exponential of I to pi k minus j and 1. This part here is equal to cosine of 2 pi k minus j plus I sine of 2 pi, just by definition of this complex exponential. And now realize that this is an integer, so this by periodicity of the cosine, this is just cosine of 0, which is equal to 1, and this is sine of 0, which is equal to 0. So basically all of this is just equal to 1, 1 minus 1 is 0. This means that these complex sinusoids with different frequencies are indeed orthogonal. So now if we want to, now let's remember a basic result in linear algebra that tells us how to express a vector x in terms of a linear combination of n orthonormal vectors v1 to vn. We want to approximate x, as a linear combination of such vectors, what we need to do is we take the inner product with the orthonormal vectors. That gives us a coefficient, and then we scale each of them by that coefficient. Okay, this is just basic linear algebra. This is the way that you can project a vector on the span of a group of other vectors. So if we want to project the signal x onto the span of n sinusoids, we're going to have to normalize the sinusoids so that they are indeed not only orthogonal but orthonormal, so they're normalized. So this is why we have this 1 over square root of t. We're going to take the inner product between x and the normalized sinusoid and then multiply it by the normalized sinusoid. This simplifies to just taking 1 over t out and taking the inner product with the sinusoids and then scaling the sinusoid. And this is essentially the Fourier series. This is all it is. So let's define it a bit more formally. The Fourier series coefficients of a function x that lies between that is defined on an interval from 0 to t is equal to the inner product between x and a complex sinusoid of frequency k over t. And the way we can recover the approximation, so first we consider approximations up until a certain maximum frequency that is often called a cutoff frequency in signal processing. If you just want an approximation up to that maximum frequency, what you do is you sum up all those components weighted by the corresponding coefficient. Remember that you need this 1 over t because the norm of each of the sinusoids is square root of t. And this gives you this approximation of the function up until that frequency. It's important to emphasize that we need to include these negative frequencies to account for possible shifts in the different components. If you take the maximum frequency to infinity, then you obtain an approximation of the function in terms of sinusoids of arbitrarily high frequencies. It turns out that actually allows you to completely to represent the signal exactly in the limit, which means that these basis functions that we have built using sinusoids that had periods which were multiples of t, where t is the length of the interval, that's a complete representation. It can allow you to approximate any function you want that is square integrable. However, we're not going to prove this result. It's beyond the scope of the course, but this shows that it's a complete basis in that sense. It can represent any function that lies between 0 and t as long as it's square integrable. Okay, so now let's take a look at our electrocardiogram. This is a real signal. We're going to take a look at its Fourier coefficients for different values of k, of the frequency k. These Fourier coefficients are complex numbers, so let's think a little bit about how to interpret them. They're going to have a certain magnitude, and then they're going to have a certain phase. The magnitudes tell us how much energy there is in each of the frequencies. So here, the frequencies, by the way, here we're going to represent them with hertz. A sinusoid of frequency equal to 1 hertz has a period that is equal to 1 second. Sinusoid with frequency 10 hertz has a period that is equal to 1 over 10 seconds. Okay, so that you know what this unit means. Here we see that most of the energy is in the low frequencies. And there's also an interesting component here at 50 hertz. So you might start thinking why there is this weird component here in the electrocardiogram. Something that you might realize is that the magnitude of the Fourier coefficients is even in the sense that when we look at positive and negative values of the same frequency, the magnitude is the same. And this is not a coincidence. It's because it's a real signal. We'll show it in a moment. Because again, we need to include these negative frequencies because the coefficients corresponding to those negative frequencies allow us to to account for possible phase shifts in each of the components. This will become clearer in a moment. This is what the phase looks like. The phase is actually pretty difficult to interpret when you just look at it. Okay, but that's by phase I mean this guy here when you take the polar representation of the Fourier coefficients. Okay, so again, the electrocardiogram is a real valued signal, and for those, there's a very special relationship between the Fourier coefficient at frequency k and at minus k. Okay, and remember, again, I do want to emphasize this as much as I can. We're including these negative frequencies because we have to account for the fact that we might be representing sinusoidal components with arbitrary phases. Okay, so let's take a look at this situation. So we have that the magnitude, we're going to call it alpha k, and the phase, we're going to call it psi of k. Okay, so psi k. Sorry, like I got stuck with that. Okay, so now let's see what's if the coefficient corresponding to the kth frequency is equal to this, what is the coefficient corresponding to a frequency of minus k? By definition, it's equal to this. Okay, so notice that there's a plus here because we're taking an inner product with the complex exponential with frequency minus k over t, and we take the complex conjugate because it's the inner product. Okay, so now, because this guy is real, we can just say that this is equal to taking the conjugate of this whole thing and putting a minus here. Okay, and this only works because this guy is real. But if you realize, this is exactly equal to the Fourier coefficient corresponding to the frequency k. So this shows you that the coefficient that you're going to get for frequency minus k is just the complex conjugate of the coefficient that you're going to get for frequency k if the signal is real valued, which means that the phases are going to, the magnitudes are going to be the same, and the phases is you just have to multiply by -1. This is going to be very useful because now we are going to be able to merge the components corresponding to frequency minus k and k to produce a more intuitive representation of the Fourier series. How do we do that? We basically look at the component corresponding to frequency k and the component corresponding to frequency minus k. We take the coefficient, we multiply it by the corresponding complex exponential, and we sum them together. And again, this is only for real valued signals for which what we said before holds. Okay, and what we said before is that they're going to have the same magnitude. Okay, this term has the same magnitude and the phase is multiplied by -1. The phase is multiplied by -1. So now, when we sum up these two components, we have this situation where we can take alpha k out. Now we have the sum of these two complex exponentials, where this is cosine of 2 pi kt over t plus alpha k. Actually, I might have written it here. No, I have not. So I was lazy. So now this laziness is coming back to haunt me. Okay, but just by definition, this is what this is. And this guy is equal to cosine of minus 2 pi kt over t, but remember that cosine of minus x is equal to cosine of x. And now minus I sine of 2 pi kt plus psi k. So these two sinus, like the sine component, cancels out, and we get that is equal to 2 alpha k times a real valued cosine with a certain phase shift. And this is why we need both the component from the component k and minus k in order to be able to represent those phase shifts. The cool thing now is that if we do this for every k, we get a representation where the whole Fourier series can be represented if of course, only if the signal is real, as a sum of cosines, okay, with a certain frequency, a certain phase shift, and a certain amplitude. Okay, and this is a lot more intuitive if you're going to plot the individual components that if you had to basically somehow plot the real and imaginary parts. We're going to going to show you some of these components for the electrocardiogram. Also realize that the component that's 0, you don't do this because there's no negative part corresponding to 0. Okay. There you basically just have a constant function. Okay, so these are the different components. This is the constant component. And now we have the very first, like k equals 1. It corresponds to this guy, which has a period of 8 seconds, which is t in the case of the electrocardiogram, as promised. This is how big that component is. Again, it's going to be shifted according to the values of the Fourier coefficients at k equals 1. And now I'm showing you, like higher components that have higher frequencies. For example, this guy at 2 Hertz. This means that there's 2 periods of that within 1 second. Okay, so you can see it here. All of these are components that if you add them together, you can build back the electrocardiogram. So this is what I'm showing you here. If you add up components up to 0, 1, and this is k equals to, I think, 16 or something. Okay, I think that's right. Anyways, I'm getting stuck there, whatever, like this up to a certain kc. And you can see how you approximate the function increasingly well as you use higher and higher frequencies. This is even higher frequencies. This is the component at 50 Hertz that we had seen before that is quite prominent. And this is the approximation up to these different frequencies. Something interesting to note is that, look at the approximation, at up to 10 Hertz. It clearly misses some parts. When you reach 50 Hertz, the approximation is almost perfect. Okay. So this is just to show you how the Fourier series slowly starts approximating the function really, really well. Oops. Oh no. Yeah, there you go. Okay, so now we're going to see how to use the Fourier series representation to manipulate a signal in a way that is useful to us. So this is the electrocardiogram data. When doctors want to look at this to interpret, the heart activity of a patient, they want to look for features that look like this. Okay, so they're called PR interval, PR segment. Have no idea actually what these things mean, but they want to see a signal like that. But instead, we're showing them a signal that does like this, at a much slower frequency than the heartbeats. And this is called baseline wandering, and it's due to the equipment that was used to measure the signal. So these slow fluctuations have nothing to do with heart activity, and therefore we would like to eliminate them. When we look at the Fourier coefficients, we know that the culprits are going to be low frequencies, right? Because this is something that varies very slowly. So now I would want you to stop the video and think, how do I use the Fourier series representation to remove that? Okay, so think about it. And removing or attenuating certain frequency components of a signal, that's called filtering. In this case, we want to remove low frequencies, and that's called high-pass filtering. The idea is that we approximate the signal in terms of its Fourier series up to like a very high frequency so that the approximation is very good. And then what we do is we say, okay, I want to take some, frequency here, okay, like a band here between minus k thresh and k thresh, and I want to throw that away. You just eliminate this, not include this at all. And that's exactly what we do. We just take the Fourier coefficients between minus k max and minus k thresh and k thresh and k max, and we ignore the rest. Okay, so this is how this looks. We have eliminated this band. And now we reconstruct the signal. And when we reconstruct it, boom, we have eliminated the baseline wandering. And this is, again, is very standard. Like in signal processing, we do this all over the place in order to do data pre-processing. Okay, like, are we completely happy? We're not completely happy because we still see this, like some high, like these noisy, high frequency oscillations here that clearly do not correspond to heart activity because they're way too fast. And this is precisely this term here at 50 hertz that I was talking about before. So maybe think a little bit more, where do you think that comes from? And where that comes from, I will tell you, is actually from the power line. Okay, so that's why it says here electric grid interference. The power line actually operates at a certain frequency, 50 hertz, depending on the country. In some other countries, it might be different. And it often pollutes signals that you're measuring electrically. Okay, and this is exactly where that is coming from, and we would like to eliminate it. So think about how you would use the Fourier series to eliminate that component. Think about it for a moment. And it's exactly the same idea that we apply to remove the baseline. Wondering, what we're going to do is we're going to basically define a beginning and an end of, a beginning and an end of that band, and we're going to remove everything that is in between. Okay, so here, so you see that you had that there. We're going to actually remove those coefficients. Here you can see that they have been removed, and we're going to add up all coefficients except the ones that are here, except these ones, and these ones. And we're going to reconstruct the signal without including those. This is called band stop filtering in the literature, because you're this one, like you're eliminating this band around 50 hertz. And when you do that, boom, you get a filtered electrocardiogram that does not have these fluctuations. Just to remind you, this is how it looked before removing the component at 50 hertz. And now you can give it to a doctor, and they can interpret what's going on with the heart of the patient. Okay, because now it's much easier to look for the relevant features of the electrocardiogram. Okay, so what have we learned? We've learned that complex exponentials with different frequencies form an orthogonal basis, and that allows us to represent signals in terms of sinusoids and account for arbitrary phases. And then we can use this representation to filter different components of the signals and extract in order to pre-process them so that we can then analyze them better. Thank you very much.